So hello everyone, in this lecture of VLSI, and in the last few lectures we started about the threshold voltage. So we are in the final discussion of like how to derive the threshold voltage. So let's see, let's complete the today's discussion and let's complete this threshold voltage derivation. So in the last class we saw this particular thing that when we apply various type of voltages at the gate terminal, and the gate terminal voltage if is changing, so with that change in voltage, what happens underneath the gate? First of all, it operates in the accumulation region, then depleted, then the charges gets depleted, and then the inversion region is formed. And with this particular things, the energy bands in the semiconductor also shifts near the surface. So the band bending takes place. And we saw that what is the maximum band bending can take place when the voltage at the Vg is positive and large. That is, it is like a little higher value. And in that case, we also saw that what is the maximum depth which we can get of the depletion region. So after this all discussion, let's move on to the another final thing. So the charge density, the depletion charge density, because of the acceptor ions, okay, near the surface is this is what we get. So this is charge density. When I say it is charge density per unit area. So charge per unit area, and it is coming because of the unit of this doping concentration. So this particular formula we have seen in the last class, that how to get this. So the depletion charge density is this much. It is given by minus of under root 2q and A, the doping concentration, into the dielectric constant of material, whatever material you are using, into the Fermi potential. Okay. So this is what it is. Then the inversion phenomena occurs at the surface, and this gives in turns this in turns is responsible for formation of the N channel, okay, in the region, and that's near the surface. So now let's see, if we move on to the, I mean, this is what our structure is, and this is how the symbols for this is. If you're using an NMOS, then the symbol for the NMOS is something like this: 4-terminal device. Okay. Usually this 4-terminal symbol is used in analog applications. In digital also that this circuit, this symbol is used, but if like your body and source are connected with at the same potential, then you don't use this 4-terminal symbol. Rather you use a 3-terminal symbol in that case. Okay. And further it is simplified in some of the circuits. You see this as well, that we don't use even this arrow, okay, because the symbol, the bubble at the gate itself differentiate between the NMOS and the PMOS, so no need to put a extra arrow here. So that is also been done. So that is what the symbols for this. And the top diagram, you can see that your this gate and source and the drain. Okay. So if it is an NMOS, then the source and drain regions will be N, whereas if it is a PMOS, then this source and drain region will be P, and the substrate will be exactly opposite. So if it is NMOS, then the substrate will be P. If it is a PMOS, then the substrate will be N. Whereas you grow oxide here at the top. How this being done? This we will see in the next unit when we will see about the fabrication. And then over that you fabricate a polysilicon or a metal gate, okay, and then you form the connection. So this is what the structure of an N-channel MOSFET looks like. Now let's move on to the final discussion for the particular thing which we have, for the threshold voltage. For we have toiled so far in the last 2 lectures to understand the things. So let's jump into this, that how to get this threshold voltage. So you see, this threshold voltage is basically is like this is what we have seen, that when we keep on increasing the channel voltage, this gate voltage, then what happens? Initially accumulation, then depletion, and then inversion. Okay. So this takes place, and what we saw is like what is the, I mean, when we keep on increasing the voltage, so first the depletion region is formed. So to form the depletion region, what is the maximum voltage we have to apply, and then the surface inversion is also required. Okay, and this, like, initially we will consider everything when your body is at ground, when you are not connected body with respect to source, because all the voltages in MOSFET will be measured with respect to source. So body is at ground, source is also at ground, drain is also at ground, and you will change only the gate voltage. Okay, so this is what we have discussed so far in our last two lectures, that the gate was the, I mean, that is why we have considered the two terminal device, because the rest of the other terminals, out of the total four terminals, the rest of the three terminals are connected to the ground, and only the gate terminal, we are changing the potential at the gate terminal. Okay, so if the gate voltage is less than a certain voltage, which is called as the threshold voltage, then there will be no channel formation and there will be no current flow between the source and the drain. But if the gate to source voltage, if the gate voltage, if the gate to source voltage, obviously because all the voltages are measured with respect to source, so if the gate voltage is greater than threshold voltage, then only the current, the channel formation will take place and the current will form. So let's see, this channel formation is like, on what factors this channel formation is responsible. So now we will see all the things which are responsible to, I mean, responsible for this particular threshold voltage. That whatever voltage we apply, we have to apply on the gate, so that the current flow is possible between the drain and the source. So what are the things? So the first thing is, let's say, as you already know, in the last discussion we saw that we use different materials to form the CMOS structure. So the different materials have the different work function, and among the material itself, if you see, so there'll be work function difference between the different materials, and this work function difference is responsible for one of the, I mean, this is one of the factor for your threshold voltage. So basically your threshold voltage have some factors which are combining or which are combining together to give you overall threshold voltage. So one factor is your work function difference between the materials. So work function difference is like, because of that only the energy band bending was taking place, isn't it? And then you have done all the things to make the voltages like flat, flat band again. So you have to make the bands flat. So for that you have applied some voltages and some things you have done. So work function difference between the material which you are using at the gate, the metal or the polysilicon which you are using, and the semiconductor. So the work function difference between this, which is also called as phi GC. Okay, so work function difference. So here, I mean, if you want to calculate the phi GC, that is the work function difference between the gate and the channel, then this is like found by by just difference, I mean, put the work function of the substrate and the work function of the metal which you are using, and take the difference of this. So whatever metal you are using, so for that you should know the work function, and whatever substrate, whichever type of material you are using in the substrate, you should know the work function for that as well. So if you take the work function difference of this two, then we get this particular phi GC. In numericals you may require, okay. Theoretically, you have to calculate these things. Then if you are using something like polysilicon, then you use the polysilicon instead of metal. Okay, so that is what is shown here in this formula. So this is one of the reason. Then the another reason is, see, I mean, this particular thing should have been shown later, but let's discuss this, because you see what is happening. First, the structure is formed, and as you have not applied any voltage, still there will be work function difference between the metals, and this phenomena will be there. Okay, then once this is formed, then later on when you keep on increasing the voltage, then something happens. So first accumulation, and then accumulation we are not considering because that is in the voltage is less than 0, okay, in case of NMOSes. But if the gate voltage is positive, so then first depletion takes place. And in depletion, so let's consider this. I mean, I'll come back to this point number 2 later, but let's consider that then that when the depletion takes place, when the depletion region is formed, then in that case, how much is the charge which is there and what amount of voltage will require to replace this charge? Okay, because you see, that much amount of voltage will be required. I mean, some amount of voltage will be required to replace this particular, to deplete the region. Okay, and how much voltage will be required, that will depend upon this charge. So this we have derived already. Okay, and this is, we are considering with like body is ground. Okay, so you see, if the body is ground, then this particular thing we represent it, we represent with VQ0, okay, or QB0. If we are in general talking about this amount of depletion region charge because of the acceptor ions, okay, because of the immobile acceptor ions, so we just drop this 0, okay, from the suffix. Then from this we drop this 0 from the subscript. So this Q0, I mean Q in general, if we write for any source to body voltage, for any, if the body is connected at certain other voltage uh, apart from the ground, so then you write, you include this VSB term here. And the reason why this VSB term is added with this 2 phi f term is because you see, this 2 phi f is because of when the body is grounded. Okay, now when the body is at certain voltage, then obviously this voltage will add to this voltage. Okay, because this phi f is now changing. Okay, it is like shifting this particular voltage, because earlier it was at ground, you are considering this phi f, 2 phi f with respect to ground. Okay, now it is like not ground, certain voltage, so you will see this voltage accumulated with this. Okay, so that is why this particular thing is added here. It will take, it will like depend upon which type of voltage you are using here. If it is positive, then it will be added. If it is negative, then it will be subtracted. Okay, and this Q is basically your charge density, that is the charge density per unit area. If you just check the unit, then you will find that it is Q is the charge density per unit area. And if we just want to find the voltage, the amount of voltage we want, so we know that Q is equal to Cox. So Q is equal to this particular thing, Q is equal to CV. Q is equal to CV we know. So if we just take this Q upon C, because we want voltage, isn't it? Voltage which we have to apply on the gate terminal. So the amount of voltage you can find by dividing this Q by C. Okay, so QB by C. QB is like body. So whatever voltage or whatever charge is there in the depletion region of the body, that is why it is written QB. So QB0 is when your substrate is, when your body is at ground potential. Whereas in general, if body is at certain voltage, then you denote it by QB. Okay, and the other, this capacitor per unit area again. Okay, so capacitor per unit area is defined as like Cox, which is epsilon ox upon T ox. Okay, so thickness of the oxide. So this is what the oxide thickness is here. Then let's move on to the, so first the depletion region is formed, and now let's move on to the another this. So first the inversion, first the depletion region is formed. Once the depletion region is formed, then you have to apply some voltage for forming the surface inversion, for inverting the surface. And how much voltage that surface inversion will require? It will require this 2 phi f voltage. Okay, so minus of 2 phi f. Phi f is your this surface potential. Okay, so Fermi potential of this. So we have seen this, what is 2 phi f earlier. So this 2 phi f amount will be required to invert the surface. Okay, so how you define this particular surface inversion? This is the amount of voltage which will be required. I mean, this will depend upon the electron density. Okay, so the electron density at the surface should be equal to the electron density at the bulk. So when this electron density of the electrons at the surface becomes equal to the electron density of the holes, so that time only the surface inversion takes place. And to do this, that is why your phi f become equal to phi s. In the last slides and the last class we have seen that why this phi f becomes equal to phi s, at that time only the surface inversion takes place. So this is what the reason is. So for surface inversion we have taken this minus 2 phi f here. So this is what the reasons are, and then let's move on to the fourth component. So we saw that there are three, up till now we have saw the three reasons are there. So work function difference, then the depletion region formation, then the surface region formation, then the surface inversion formation. Okay, so these three components are like responsible for threshold voltage up till now. The fourth component is like we have not seen that, but whenever like you grow a oxide over the this substrate, so then there will be some trapped charges which comes there. Okay, some positive fixed positive charges which comes there in the this oxide layer, and you have to compensate for that as well. You have to something, I mean you have to, because you have to form a inversion layer. So theoretically you may like not consider them, but practically when you will actually apply the voltage, then if you just consider the above three components, then your practical voltage, practically the voltage which you will require at the gate for surface inversion, for the conduction, for the formation of the channel, will be quite larger than what you have calculated calculating the other three components. And the reason for that is because there are some trapped charges which are there in the oxide and the substrate interface. So oxide substrate interface holds some charges at the in between, okay, some positive charges, and we have to do something, I mean to offset for that as well. So to offset that, we require voltage corresponding to that trapped charges. So that let's assume that the trapped charges density is qox. Okay, so the charge in that particular trapped charges is the trapped charge density is approximately, let's say, qox in the oxide. So if we want to find the voltage for that, again we can do the same thing what we have done in the for the in the point 3. So that is what we again do. So qox upon cox. Okay, and why we are like using minus here for all the things? Because we are considering the electrons. So electrons will have negative charges. So that is why this minus is coming everywhere. Okay, if you are using holes, then the symbol will change accordingly, right? So these are the four things which give rise to your threshold voltage, and that is why, because of this four things, you have to apply some threshold voltage to form the to invert the channel underneath the gate. Okay, and you can see that this all things depends upon your doping concentration. Okay, if like your trap concentration, if the amount of charges trapped in the this oxide surface interface increases, then you have to apply more voltage. Okay, so you see, if you just combine all these four things, then your threshold voltage equation looks something like this. Okay, so these are the four things: phi gc, work function difference, then this surface inversion, okay, surface inversion part, surface inversion component, then this is your this depletion region component, then this is your trapped charge component, and all of them were having this minus along with that. So if you add them up together, then this minus will come. Okay, so actually we are not subtracting, we are adding them up together. Okay, so this is what the general equation of threshold will be. So you should remember this equation, and if you further solve this equation, okay, so this is like the equation. So this is one of the most important thing. Okay, so in general, if you want to find any, if you want to find the threshold voltage for any device, whether it is a semiconductor device, this particular silicon device, or if you have formed the device with any other material as well, okay, gallium arsenide device or something, so then you have to find this particular components. Once you find these components, then only you will be able to compute this threshold voltage. Okay, and this threshold voltage component is important because you see later on we will see the techniques to modify this threshold voltage also. That if you want to change the threshold voltage of a device, then by doping in the channel, okay, by in the surface at the near the surface, you can dope the material with some impurities, okay, in that particular region, and then you can manipulate the threshold voltage also. So that is what is being done nowadays. So the threshold voltage is manipulated nowadays. So for NMOS you get a for NMOS usually the threshold voltage should be positive, okay, because you will require some electrons, some like holes to get some electrons to get attracted. So to attract the electrons, you will require negative charges. So you require positive charge at the gate. But with doping in the channel, you can make it positive. You can in fact reduce it, increase it, or you can change its polarity also. Okay, in NMOS devices you may require negative voltage, okay, to attract the electrons. That will depend, that may be because of the doping concentration which you are using near the surface. So that particular thing, though we have not discussed here in this particular thing in lecture, but you will find this if you just read the book, you will find this particular thing there. So that some doping you can do at the surface in the channel region itself while forming the device. So this equation forms is a very important equation. Okay. Now, based on this equation, for this equation, if you, I mean, this is the general equation. So if you write this equation when the body is grounded, then you call it Vt0. Okay. The same equation if it is written for for the case when your body is at ground, then you call this equation, this particular thing, as Vt0. But if the same equation is written for in general, okay, the body can be at any volt, any potential, then this equation will be termed as Vt. Okay, so the same equation can be written as Vt0 or Vt. Now, if you want to just have a relationship between Vt and Vt0, okay, see, Vt will depend upon, like, it should vary. So there should be a fixed part because of when the body is grounded at that time, and if you are like applying some voltage in the body, so then that should change. Okay, whether it should increase or decrease, that we will see later, but it should, I mean, there should be a relation between in general equation when you apply certain voltage to the body and when you have not applied any voltage. So that relationship, if we try to find, so then you see this is actually the relation. And how to find this? In this particular equation, if you just substitute the things like this, okay, just subtract and add and subtract the things with this in this particular thing. Okay, so this is the general equation. So I have written the expression for this, that how to get this, because you may find this difficult to understand sometimes. So in this equation, in this particular equation, if you take this equation, and in this equation, if we just add and subtract QB0 upon Cox, okay, QB0 upon Cox. So this particular component is added and subtracted in this equation. So the equation will remain same if you add and subtract the same component. So then if you do this, then you can write the equation in this form, because this particular thing will be your 5gc minus 2phi-f minus QB0 QB0 upon Cox minus Qox upon Cox. This will become your Vt0. Okay, and this Vt0, because Vt0 will be like this only. Okay, so this is your Vt0, and this Vt0 along with this you can write it as in general Vt. So this is the equation for your Vt. Now, in this equation, if you further solve it, substituting the things which we have derived for QB and QB0, okay, so you can find it as this. So you see, let's see this equation. So this is your equation. So if you just solve this, then this equation, substituting the values which we have found for QB and QB0, if you just substitute them, then you will find that the equation will look something like this. Some 2phi-f plus VSB term will come because of this QB part, and QB0 will have this VSB part will not be there. So 2phi-f part, and then you are subtracting them together. Okay, so that is what you are doing, and some constant will come because both the equations will have this constant part. So you are taking this constant part outside, 2 under root 2 cube Na epsilon Si upon Cox, and this particular thing is denoted by gamma, which is also called the body coefficient. Okay, or the this. Okay, so this is called your substrate bias coefficient, or the body effect. Okay, so this gamma is denoted by body effect. So this is what your this body effect. So if you just want to find the body effect for a particular device, then you have to calculate this thing. Okay, if you want to calculate the threshold voltage, then you should know the threshold voltage when the body is grounded. Then you use this body bias component or the body effect component. Then this is a constant sort of thing, because you see there is nothing, there is no variable. All the things are like fixed. So for a device, this will be fixed. This will be a constant. So that is why we are calling this as a constant. So you should know this body constant, body effect constant. Okay, body effect coefficient, and then whatever this Fermi potential you have, this and this VSB. So you have to this like whatever voltage you are using. So this is the general equation which you get. Okay, and in this equation, if you will just see that if you make VSB is equal to 0, so if you are like making the body again to 0, so then you will see that this again Vt will become equal to Vt0, because this particular part will reduce to 0. Okay, because if VSB is equal to 0, then this is equal to exactly equal to this. Okay, and this will be cancelled. So VT will be equal to VT0 when your VSB is equal to 0. So body is at is if the body is at same potential with respect to source. Okay, so if the body and source are at same potential, then your VT will be equal to VT0. But if the body and source are not at the same potential, then you will have some body effect into it. So you also understand with this discussion that what is body effect and how it comes in picture. So body effect actually is because of the voltage which you apply over to the onto the body, okay, with respect to the source. So if there is a difference between body and source, some body effect will come into the picture, and that will change your threshold voltage. So it will, like, if the body is connected at certain positive voltage, then the threshold voltage will increase, right? If the body is connected at some negative voltage in case of NMOS, then the body effect, then the threshold voltage will reduce. So you see, actually the body is like, that is why it is, the body is also sometimes called as the second gate. Okay, because it is used to, I mean, you can use the body to change the threshold voltage. Apart from, I mean, apart from what I have told you earlier, that you can use the doping in the surface, doping at the surface in the channel itself, not anywhere else. So that also can help you to manipulate the threshold voltage. But if you're using a device, then you can use the body voltage. You can use the body. If you tie the voltage, if you connect the body to a different voltage, then you can change the threshold voltage also. So that is what the thing you have. So that is why the body is also called as the second gate for the device. So this was all about this thing. So in general, you have seen all the things. So the earlier equation which we have seen here is important, and along with that, this equation is also important. So this equation will become will be important to calculate your threshold voltage. So use this equation to compute the threshold voltage for any device which you want to. Okay, theoretically or practically, if you are using in, okay, in numericals also you may require this. So this was the discussion all about your NMOS. Now suppose you are using a PMOS, so then these parameters you will compute them in the same way, but only the thing which will change will be the symbol, because because already I have told you that for the PMOS, the charge, this particular thing will become positive now. Okay, because in case of NMOSes, you were calculating the QB0, the charge density, the surface charge density. So then that charge density, the depletion region charge density, whatever we have calculated, it was because of the holes, was because of the electrons. So that is why we've used a negative sign there. In case of holes, in case of PMOS, that will be the charge carriers will be holes, obviously, and then the things will be opposite. So you can see that is what is shown in this particular slide, that whatever parameters, the sign which you have used for NMOS, the sign for PMOS will change for this particular parameters. So phi f sign will change, will become positive. QB Q0, this QB and QB0 charge, this sign will also be positive, whereas the gamma and the body effect coefficient, this source to body voltage will be negative. Okay, so this is what it is. So I hope the things are clear up till now, and this is this type of numericals you may see. So you will get the chance to solve. I mean, this is the numerical which I have taken from the book directly, the image of that numerical. So you can try that numerical, and similar type of numericals we will solve in the tutorial class as well. Okay, so in the tutorial class you will see in this particular week, you will see the threshold voltage, how to calculate the threshold voltage with respect to these numericals. So in this numerical is a very simple numerical what I have taken. So you will see that you have to calculate the threshold voltage when the body is grounded, right? And the material used is the polysilicon. So for this particular polysilicon, the doping concentrations are also given. So with the following substrate doping concentration is this. So you have the substrate, because the substrate is of, let's say, p type, so the doping concentration is given, whereas the polysilicon is of, should be a metal, so it should be it should have pentavalent impurity. Okay, so the donor type of. So you see this is having ND. So the doping concentration for both of them is given, and this is given to compute your 5GCLs. Okay, so you can like calculate the 5GC from this. So you can use this particular things wherever it is required. So you have seen the formulas there, and you can use this into those formulas to compute the things. And then the gate oxide thickness is also given, and in this numerical, the oxide interface fixed charge density is also given. So basically, NOx is given. So you can use this as to compute the QOx. Okay, so QOx, whatever is the trapped charge density, the amount of trapped charges there. And COx you can also calculate for this, because you see in this material epsilon is not given. Okay, because you will require to compute the COx as well, which is COx is equal to epsilon ox upon Tox. So to compute that, you will require epsilon ox. So in numerical, sometimes you may find that the epsilon value is not given, or some of the parameters are not given. These parameters are very well known, and you should remember this particular things. So that is why this particular thing, sometimes you may not find them here in the numericals. So you should remember those things, and if you don't remember, you just take a practical some typical values which is used for these materials, and based on this you can compute the things for them. Okay, so this is like a very simple numerical. This will be a very simple numerical. You have to just substitute the values in the previous equation which we have solved, which you have derived, right? And you will get the answer. So you'll try this numerical in the by your own, and if you have doubt, you can ask in the tutorial class, okay? Or you can ask to me as well. Okay, so let's move on to the final slides, and let's summarize the things. So this is what we have seen. So your NMOS device will have something like this. 3 terminals are shown here, but actually the device will have 4 terminals. The body terminal is not shown here, but it will have it. And you can see that the substrate is of p-type, and in that substrate you form 2 N regions and a gate terminal. Okay, so the gate terminal is between source and drain. So this is your NMOS. The symbol for NMOS is this. Okay, it is shown here without bubble, you can see, and no arrows are there. And this symbol is like when gate is at 0 voltage. When you don't apply any voltage at gate, then the switch, then there is no channel, and the switch works as an off. Okay, so it will work as a switch and it will be off. The switch is off. So the NMOS will work as a switch. So and the switch will be controlled by this gate voltage. Okay, so the gate voltage, so you just assume, I mean in the circuits wherever this NMOS is used, you assume it as a switch. NMOS and PMOS both will be assumed as a switch. Okay, for simplicity you can assume them as a switch, and the switch will become on and off. Okay, and this on and off will be controlled by this gate voltage only. So when the gate voltage is less than threshold, basically when you are saying it is 0, you are saying that when the gate voltage is less than threshold, then your switch should be off ideally. Okay, practically there will be some current, but that current will be very small. And when your gate voltage, when you apply some gate voltage above threshold voltage, then you form a connection between the drain and the source, that is your switch is on, right? So that is what the difference is. Now in case of PMOS, the things will be exactly opposite. Okay, so whatever you have seen here, the bulk now will be of N type, whereas these regions, source and drain regions, will be of P type. Okay, whereas the polysilicon will be same, SiO2 layer will also be same, and you form a connection again. And the symbol for this SiO2, this P type material is this. Okay, so this is the symbol which you use here, and this symbol again will work exactly opposite. Okay, so you see this. In case of NMOS, when the threshold voltage is greater than threshold, when the gate voltage is greater than threshold voltage, then only the gate was on. Here in this case, if you just talk in terms of the not in the magnitude form I am talking, I'm just talking about the actual value, which will be negative in case of PMOSs. Okay, so when gate is equal to 0, that time when gate is less than threshold voltage, then the device will be on, whereas when you apply some positive voltage on the gate, then the gate will be off. Okay, not gate, the device will be off. This is the basic thing, and we will understand when we will use the circuit, when we will move on to the circuits. At that time you will understand the things more clearly, that how these devices are working and what is the importance of this particular thing, the symbol, and how the switch analogy becomes important for this circuits. So uh, in the conclusion, just we have seen that so far that the device with change in gate voltage, the device works in different regions. So first region is accumulation region. When you apply, when your gate voltage is less than zero, so some charge gets attracted in the this in the this, because this polysilicon is your negative, so some positive charge get attracted near the surface, and this is called as the accumulation region. But when your gate voltage you keep on increasing and your gate voltage is a small positive voltage which is less than threshold voltage, then you form a depletion region here. So actually this is also happening. So this way also you can understand the things. Okay, when this Vg is greater than the threshold voltage, then you have formed a inversion layer. Okay, so accumulation, depletion and inversion. And how much inverted the layer will be, that will depend upon how much gate voltage you have applied above the threshold voltage. So that is also called as the excess gate channel voltage. So that excess gate channel voltage is nothing but VGC minus VT. Okay, so the inversion layer, the depth of the inversion layer will be more if you are if you apply higher gate voltages on the gate terminal. So that is what it was. So this discussion is like about this threshold voltage formation, and we will start the next class from this discussion, because in the next class we will start discussing that how to derive the drain current. So what will be the amount of drain current which will flow, so on what phenomena this drain current will depend. So that we will see the particular discussion in the next class. So now I think you may be able to connect the things which you were like missing in the during the class, that why this we are calculating this energy band diagrams. Okay, and we are like showing this energy band diagrams discussion. So now with this all discussion you will be you are more clear, I think, that why this energy band diagrams are shown to you. And the good thing is, like, if you're not able to understand them, then nothing to worry, because those energy band diagrams will not be used too frequently in the discussions. Later on, while discussing the things, while discussing the current flow, we have to just use the drain current equation in the circuits, and that don't require this energy band bending diagrams and all those things there. But as I have told already, that particular thing is required to understand this threshold voltage formation. And once you got the threshold voltage, then or that on what factors it depends, then you can use directly the threshold voltage, and you don't even have to derive the threshold voltage. Okay, that threshold voltage is required, I mean you require to derive it only when you are forming the device at the very first time. Okay, in the fabrication, at the fabrication level, or when you are like researching in the field, in that field. But once you have a device, then that threshold voltage is fixed. Okay, and you have to just use that threshold voltage in the drain current equations. Okay, so if you don't understand that particular thing also, then nothing to worry that much. Okay, so this is what about this. So let's end the today's class here, and we will meet in the next class with the drain current equation. So thank you everyone for listening.